You ever get the feeling that math is this secret language that only a few people get to speak? Well, today we're going to change that. We're going to dive into the simple yet powerful ideas that math uses to handle everything from mind-bogglingly huge numbers to incredibly tiny ones. Okay, so let's kick things off with a number you hear thrown around constantly: a billion. We hear it in the news, we see it in headlines about tech companies, but have you ever just stopped and tried to picture what 1 billion actually is? And when you actually write it out, man, it's just a 1 followed by this huge parade of zeros. 9 of them. It's awkward to write, it's easy to misread, and let's be real, if you miss just one of those zeros, your whole calculation is completely wrong. Now let's jump all the way to the other end of the scale. I'm talking about the microscopic world. What about something so small it's almost impossible to even think about, like the electrical charge of a single electron? I mean, just look at that. You've got to wade through 18 zeros after the decimal point before you even get to a number that isn't zero. It's the exact same problem as the billion, just flipped on its head. Our regular way of writing numbers just isn't built for this, right? There has to be a better way. And thankfully, there is. This is where the real elegance of math steps in to give us a much smarter way to handle all of this. Let's see how it works. So here's our roadmap for today. We're going to cover the basic rules, then unlock the magic of exponents for growth and their counterpart logarithms for going in reverse. And then we'll put it all together to see how it works in the real world. Let's do it. Okay, before we can build these massive mathematical skyscrapers, we got to make sure our foundation is rock solid. So we're going to do a super quick review of the basic grammar of math. These are the rules that everything else is built on. And this is such a great way to see it. That distributive rule, it's not just some random formula you have to memorize. You can actually see it. The total area of the big rectangle is the same whether you figure it out in one go or add up the two smaller pieces. It's intuitive. It just makes sense. And you know, that's really the beauty of it all. This logic is consistent. The same rules that work for whole numbers, they work for fractions too. That's what gives us a system we can actually rely on. Okay, foundation set. Now for the main event. Let's talk about exponents. This is the truly elegant solution we've been looking for. It's the language of growth, and it's the perfect tool for taming those crazy big and small numbers we saw earlier. So what is an exponent, really? Well, think of it as a super convenient shortcut. When you see a with a little n floating next to it, the a is the base number, and that n, the exponent, is just telling you, hey, multiply a by itself this many times. That's it. Simple, right? But oh, it is so powerful. And this is where things get really, really cool. Because exponents are all about multiplication, they come with these incredible built-in cheats. If you want to multiply two numbers that have the same base, you don't have to do all that long multiplication. Nope, you just add the exponents together. It's a massive shortcut. And boom, just like that, we're right back at our original problem, but this time, we've got the answer. That messy 4.9 billion becomes this clean, simple 4.9 times 10 to the power of 9. This is called scientific notation, and it doesn't just look better, it makes it so much harder to make a mistake. Now, you can use pretty much any number as a base for an exponent, but there's one number that's, well, it's special. It's the number e. Kind of like pi, it's this weird number, about 2.718, that just shows up everywhere in nature. It is the fundamental number for describing continuous growth. And when you actually graph this thing using e as the base, you get this classic shape. We call it the hockey stick of exponential growth. It starts off so slow, almost flat, and then whoosh, it just shoots for the moon. You see this pattern everywhere, from biology to finance. So let's break down what's happening on this graph. There are a few really key things to notice. The curve just keeps getting steeper and steeper, heading towards infinity. But on the other side, it gets closer and closer to zero without ever actually hitting it. It can never be negative. And one more crucial point. It always, always crosses that vertical line at the number 1. Why? Because any number to the power of 0 is 1. Okay, so exponents are amazing for showing how things grow. But what if you need to go backwards? What if you know where you ended up, but you need to figure out how long it took to get there? For that, we need the other half of this power duo, logarithms. The best way to think about this is that they're two sides of the exact same coin. The exponential form says if I start with a and multiply it x times, I get n.
The logarithm flips it around and asks, to get to n starting from a, what power did I need? It's a perfect inverse. Seriously, if you only remember one thing from this whole section, let it be this. The logarithm is the power. That's it. When you see log base 2 of 16, all it's asking is, what power do I need to raise 2 to get 16? The answer, of course, is 4. Logarithms are just power finders. All right, so that was a lot of theory. I get it. But how does any of this stuff actually work in the real world? Let's take a look at a real-deal engineering problem and see how these fundamental rules are the key to everything. So check this out. This is a problem pulled right out of an engineering math book. We're not talking about abstract ideas anymore. This is about actual pressure in a physical vessel. And to figure this out, we have to go right back to those basic rules for fractions we talked about at the very beginning. And here it is, the solution. And I love that it's handwritten, not some slick graphic. This is how the work actually gets done, right? It's a straight-up application of those simple rules to get a real, concrete answer. It's the perfect reminder that no matter how advanced things get, it always comes back to the fundamentals. So let's pull it all together. What have we really learned here? Well, we've seen that math gives us this incredible language to talk about the universe at every scale. Exponents act like the gas pedal for growth, and logarithms, they're the decoder ring that lets us work backwards. Most importantly, these aren't just abstract ideas, they're the practical tools we use to build and understand our world. So I want to leave you with a final thought. A question, really. Now that you have these tools, now that you understand this language of growth and decay, where do you see it? Maybe it's in how your savings account grows, or how a sound fades away, or even how an idea spreads online. You now have the lens to see the world a little differently. The only question is, what are you going to look at first?